So now we're going to talk about notes and waves. Draw the diagram of the wave. This distance from the top of the wave, let's start there. Top of the wave is the crest. The bottom of the wave is the trough. And these are what we call transverse waves, as opposed to when you did earthquakes in 8th grade, you talked about primary waves, the P waves. Those are push-pull waves like an accordion or a slinky. S waves are transverse waves, just like these. The distance from the resting position, which is this line here, to the top of the crest is called amplitude. And the distance from one crest to the next is the wavelength. So, wavelength, distance from crest to crest. And we use the Greek letter lambda, which looks like an upside down Y. It's lowercase l. Uppercase looks like an upside down V, to represent wavelength. Amplitude is basically wave height. When you turn up the sound on something, you're increasing the amplitude of the sound. Frequency is how often a wave comes by, and we use the Greek letter nu, N-U, which is a small n, but in the actual letter itself looks like a V. It's still a horrible V. A V that's blowing in the wind. That's pretty good. Frequency is the number of waves per second. It's a rate. The units for frequency is 1/seconds, which is also known as a hertz. The unit for wavelength is meters, although sometimes we will have it in nanometers. Speed of light is used, we use the letter C to represent speed of light, and the speed of light is a constant. This is in a vacuum. It is 3.0 times 10 to the 8 meters per second, which is why we use meters for our wavelengths. Okay. Now, as we study wavelength, we will discover that wavelength and frequency vary inversely, which means that they, as one goes up, the other goes down. All light travels at the speed of light. So all light travels at 3 times 10 to the 8th meters per second. So that relationship of wavelength and frequency can be described in this chemical equation. The speed of light is equal to the wavelength times the frequency. Thus, if you were solving for wavelength, you would take speed of light divided by frequency, and if you were solving for frequency, you would take speed of light divided by wavelength. Energy in a wave, Max Planck discovered that energy and frequency were directly related. As one went up, the other went up. But, of course, you have to convert it. Frequency and energy do not have the same units. So the way we convert that is by multiplying by something we call Planck's constant. Planck's constant is represented by the letter H. And it is 6.63 times 10 to the negative 34th joule seconds. Okay? Our units for energy are joules. Which is represented by a J. The wavelengths of visible light. Visible light, of course, is the rainbow. Newton took light, passed it through a prism, discovered that there were different types of light. So the most common acronym for this, that you guys have all probably heard of, is Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. They range from about 700 nanometers all the way down to about 400 nanometers in length. And remember that 1 nanometer is 1 trillionth of a meter, right? 1,000,000th million, billion, yes, 1 billionth. All right.
Artists from around the world come to Cape Cod in Massachusetts to paint the landscapes. They say that the light and the colors here have a unique quality. Have you ever thought about what makes the colors of the sky so different, or why there are so many different colors on the earth? All the colors in light are contained in white light. Here, I'll show you. This is a prism. A prism is a triangular-shaped piece of glass or other transparent material which separates white light into the colors of the visible spectrum: red, orange, yellow, green, blue, and violet. When light travels from air through the prism and back to air, it bends. This is called refraction. Each color of light has a different wavelength, so that each color bends at a slightly different angle as white light passes through the prism. Have you ever seen a rainbow after a rainstorm? In the sky, raindrops act like tiny prisms. They refract the sunlight, creating a rainbow consisting of all the colors of the spectrum. The visible spectrum is only a small part of the much larger electromagnetic spectrum, which includes the whole range of wavelengths, from radio waves to X-rays and gamma rays. So why do objects appear a certain color? Why is my hat blue? Is it because blue light comes directly from the spectrum and lands on this blue hat? Is blue light shining from this hat? No, not exactly. This hat, my shirt, the chair, the paintings, the flowers, all of these are considered opaque objects, which means light is unable to pass through them. Opaque objects don't produce their own light, but they do reflect the light that hits them. When light hits an opaque object, certain colors of the spectrum are absorbed, while other colors are reflected. The pigment in an object determines its color, whether it comes from a dye added to the material used to make this hat or naturally from this apple. This hat looks blue because pigments in the material reflect only those colors of light that, when combined, look blue. The other colors of the spectrum are absorbed, so you don't see them. So, the pigments in an object determine which colors are absorbed and which are reflected. If an object reflects all the colors of light, it appears white because all the colors of the spectrum combined form white light. If an object doesn't reflect any of the colors of the spectrum, in other words, if all the colors are absorbed, then the object appears black. But how do we actually see the colors that are reflected off of these objects? Light reflected from an object enters the eye through the pupil. The image then falls on the retina, the inner surface of the eye. The retina consists of specialized cells. Different cells respond to the different colors of light. As the image forms on the retina, these specialized cells transmit information about color to the brain. Of course, you don't necessarily need to know all of that to appreciate the colors of this painting. But now you know that there's more to color than meets the eye. Or is there? Can you think of some sources of white light other than the sun? If sunlight is white, why does the sky look blue? Do you think the sun shines in space? Then why does space look black? Some studies have shown that certain colors have an emotional effect on people. Do different colors affect your mood? We live in a world full of different colors. Next time you're outside, look around and see how many different colors you can find. Have you ever thought about how we're able to reproduce all these colors in paintings, photographs, magazines, and videos? We can make practically any color we want with paints, dyes, even computers. But all of the colors can be made by mixing only 3 basic colors, the primary colors. Magenta, a reddish color, yellow, and cyan, a bluish color, are the primary colors of pigment. All colors can be made from a combination of these 3 colors. By mixing pigments, we can control which colors of the spectrum are reflected back to our eyes, and thus which color or colors we see. Each of the primary colors of pigment actually reflects 2 colors of light. For example, magenta reflects blue and red light. Cyan reflects blue and green light. When magenta and cyan are mixed together, only the color that they both reflect, blue, will be seen. This is called subtractive color mixing because as more pigments are mixed together, more colors are subtracted from the spectrum, and fewer colors are reflected back to our eyes. If you mix all 3 primary colors in equal proportions, the result is black. That's because all the colors of the spectrum are absorbed and none are reflected to our eyes. The primary colors of pigment are used to print color pictures or photographs. First, a color photograph or picture is put into a special machine that separates the color image into the 3 primary colors and black. This is called color separation. The result is 4 images, each one containing only one of the primary colors, cyan, magenta, yellow, and black. By adding the color black, the overall image is sharper than if the 3 primary colors were combined to make black. The 4 separate images are then used to print the picture onto paper. The printing machine prints each color separately, one on top of the other. When all the colors are recombined, the picture is recreated. Printers need to use the true primary colors, magenta, yellow, and cyan, because they're trying to recreate a color picture or photograph using as few colors as possible. But you can make almost any color just by using red, yellow, and blue. Like this artist. She's able to make green by mixing yellow and blue paints. The primary colors of light work in a different way than the primary colors of pigment. Red, blue, and green are the primary colors of light. If a red light shines on this ball, it becomes that color. If a green light is added, guess what color it becomes? Yellow. It's probably not what you expected, but to your brain, red and green together are seen as yellow. What do you think will happen to the color when the blue light is added to red and green? Now remember, these three colors make up the primary colors of light: red, blue, and green. White light. And if you notice, these three lights produce a brighter light than just one color, or two colors combined. This is called additive color mixing, because each time we add a color, we're adding to the total amount of light that's reflected back to our eyes. A color television set uses the three primary colors of light to display color images. If you look closely at a TV screen, you'll see a pattern of red, blue, and green dots on its surface. From a distance, those red, blue, and green dots of light combine to produce full color images. Before color printing or television was even invented, the French painter Georges Seurat and other artists used a method of painting called pointillism. These artists painted tiny dots of color next to one another. When the paintings were viewed from a distance, the individual dots couldn't be seen. The person looking at the painting saw only areas of a single color. How do you think bright neon colors are made? Based on what you know about color mixing, do you think there are colors that haven't been discovered yet? Can you think of ways to make dyes from things found in nature, such as plants, vegetables, or animals? The sun is a natural source of light, but it can't be with us all the time. So, people have designed light sources to provide light at night, or in places that sunlight can't reach. This light contains everything I need if I get stuck on the side of the road. I can use this part here if I have to change a tire, this part if I need a flashlight, and this section here flashes to alert other drivers. This bulb is like an ordinary household light bulb. It's also known as an incandescent light because it produces light from heat. The light bulb contains a metal filament or wire. When electricity flows through the filament, it heats up and produces white light. Fluorescent and also neon lights are known as cool or luminescent lights because they don't use heat to produce light. Fluorescent light is produced when electricity flows through a special gas contained in a tube or bulb. The electric current causes the gas to react with a special coating on the inside of the glass tube or bulb. This reaction produces white light. Fluorescent lights are used in classrooms, stores, and sometimes at home. Because they use much less electricity, they save energy and they're less expensive to use. We call these neon lights. Neon lights are filled with neon gas, which glows bright red when electric current flows through it. But it's also possible to fill the glass tubes with other gases that produce other colors. There's another very useful type of light source, the laser. Laser stands for light amplification by stimulated emission of radiation. Well, now you see why they just call it laser. A laser is a device that produces an intense beam of light of one color. Sunlight, incandescent, and fluorescent lights contain all the colors of light, each with its own wavelength. Because each wavelength is different, they interfere with each other as they travel, causing the beam of light to spread out. Laser light, on the other hand, contains only one color, and so only one wavelength. Because it has only one wavelength, there's no interference, and the beam doesn't spread out. There are several different types of lasers. This laser consists of a glass tube with a reflective coating on each end. One end is only partially reflective. The tube contains a colored liquid. When an electric current flows through the liquid, the atoms which make up the liquid become excited. These atoms produce light that is reflected back and forth inside the tube, exciting more atoms that in turn give off more light. Eventually, the light gains enough energy to shine through the partially reflective end of the tube, and a powerful, concentrated beam of laser light is emitted from the laser. Because the liquid is a single pure color, it produces light of a single wavelength. Lasers are now used in many delicate medical procedures, like eye and brain surgery. In many procedures, lasers have replaced scalpels because they're more precise and have the unique ability to heat as they cut. The heat seals the blood vessels as the laser cuts through them. This reduces blood loss during surgery. Other kinds of lasers are used in supermarkets and other stores to speed up purchases at the checkout counter. A laser beam shines on a pattern of black bars, the barcode, printed on the item being purchased. The laser light is reflected back to a device that interprets the barcode, which contains information about the product. Lasers have even become part of the music business. Compact discs have become the most popular medium for playing music. Using a system of lenses and mirrors, the CD player shines a beam of laser light onto the narrow spiral track on the CD. As the disc spins, the laser reads the information from the disc and sends an electrical signal back to the speakers where it's changed into sound waves. Music. Compact disc technology isn't just for music lovers. CD-ROM discs for computers and laser discs of movies both use laser light to read information very accurately and at very high speeds. Lasers are also used to measure long distances extremely accurately. When the Apollo 11 astronauts landed on the moon in 1969, they left a mirror on its surface. It's still up there today. Scientists use it to reflect laser light that they shine from the Earth to the moon. By analyzing the laser light after it travels back and forth, it's possible to measure the distance between the Earth and the moon. How has artificial light changed the way we work and live? How many different machines can you think of that use lasers? What actually happens when a light bulb burns out?